Hello everyone. Now in this video we are going to develop a model regarding the LNG regasification process integration with the CO2 liquefaction process in order to recover the cold energy from the LNG regasification system and use the cold energy to convert the CO2 into liquid phase. Basically, this integration is still conceptual design, which consists the improvement of the previous design or basic design of LNG regasification process. In previous video, we utilized the glycol water to take the cold energy from the LNG regasification process or as the heating medium. And in this video, we will try to use the CO2 to recover the cold energy from the LNG regasification process and will be used to convert the CO2 into the liquefied phase so that the CO2 can be stored in much smaller of storage volume. As you can see here, I have prepared several equipment here so that this video duration can be minimized. So we can see the LNG regasification feed stream. I chose this data and assume that the LNG comes from the storage. I use the operating condition, and for the composition you can use this following data I took from the reference you can see in the description below. Actually, the LNG regasification process is the same with the previous one. So we will increase the pressure from the feed from the storage and increase to 10 bar using the LP pump or low pressure pump here, and will be increased furtherly using the HP pump or high pressure pump and achieve the pressure required of 65 bar. Practically, between these two pumps, LP and HP pump, there is a recondenser that used to cool down the BOG using the LNG from the storage or absorb the boil of gas which produced due to heat increase into our system. And the recondenser can be used to mitigate or to prevent the cavitation of this high pressure pump, or let's say we can use the recondenser as the pump suction drum. I also have prepared several equipment here, such as the heat exchanger, which will be used to cool down the CO2 and to vaporize the LNG or to convert it into the gas phase. Before we start the simulation, you can change the respective heat exchanger into the simple weighted model, and you can use the pressure drop both on cell side and tube side approximately 10 psi as initial value for this pressure drop. You can use this arrangement for all the heat exchanger. We can provide this exchanger, actually the two intercooler heat exchanger and one aftercooler heat exchanger, to regulate the temperature outlet the compressor unit. You have to provide this component splitter which represent the molecular sieve and these two flash tank in order to separate the water content from the CO2 stream after the CO2 is cooled by natural gas or cold stream here. You can also provide the component splitter here which represent the molecular sieve in order to ensure that there is no water content remaining in our CO2 system, because it can cause the plugging or hydrate formation. We can observe the CO2 stream here that we will increase the pressure and convert it into liquid phase, you can use this operating condition and you can specify the random of the mass flow here as the initial value of our CO2 stream, and we can see the composition. You can use this following data. Actually, I took this data from the reference. Oh yeah, in the beginning I also prepared the component here. You can check in the component list. I have specified several compounds here. You can follow me for the compounds we will use in this simulation. And for the fluid package, we choose the Peng-Robinson fluid package here to model our system. We can start our simulation by solving the CO2 first. So actually I want to recover the cold energy from the LNG stream and using it to convert the CO2 into the liquid phase. So we can connect this CO2 stream, CO2 feed stream from the upstream process into our compressor, and we can specify the pressure ratio. We can leave it as it is for the operating mode. Maybe we can talk deeper regarding the operating mode in another video. We can specify the pressure ratio. We can specify 3. Then let's observe the outlet temperature of the first stage compressor. We obtain that the outlet temperature from the first stage of compressor is 146, which is actually still under allowable temperature, while the recommendation maximum temperature is 150 in order to prevent the risk of failure of this compressor and maintains this compressor at safe range of temperature. So in priority of safety, we can see that the outlet temperature near the maximum allowable temperature, so we have to cool down this temperature. We can utilize the cold energy from the LNG, so we can connect this stream to our heat exchanger, LNG heat exchanger. This intercooler heat exchanger is used to minimize our energy requirement for the rotating equipment here. We can adjust the direction of this stream, and then we can specify the temperature requirement for our system here. We can leave it as it is for stream L3 and stream number 5 for the temperature, and we can specify the temperature of this stream number 4. We can specify 10 centigrade. Then we can see this stream result for stream number 4 here. Actually the aqueous phase is present in this system. It is actually mostly of the water in aqueous phase. We have to remove the water from the CO2 system using this flash tank separator to separate our water content here. We can continue our system by connecting the top product of the flash separator into the suction stream of this compressor. After the water is separated, and try to connect and specify this compressor. We can specify the pressure ratio of 3, and for operating mode we can leave it as it is. Then we can continue to connect this stream. We can see that the stream is 110 centigrade, so we will cool down this temperature using the LNG cold energy. Connect this to heat exchanger, and actually we want to cool down while we also want to separate the water content in this stream. You can specify 10 centigrade to condense the water and to minimize the power required for compressing this gas, as well as to minimize the risk of failure for this compression system. Then we can continue to connect the top product of this flash tank separator and connect it into our suction stream. There is still not connected. It has connected, and we can specify the pressure ratio of 3 here. And here the simulation result, there is the increment of pressure and the temperature at 111 centigrade due to increase of the pressure. And the target is we want to store the CO2 at 20 bar and minus 20 centigrade approximately. So we can try to connect this stream with this heat exchanger, and then we can create the outlet stream, and then we can specify 10 centigrade here.